Okay, I guess we'll get started. Thank you all for coming along. My name is Ian Clarke. This is Oscar Sandberg. Our talk is entitled Rooting in the Dark, and I guess we'll get started. Oscar and I have both been involved in peer-to-peer networks pretty much since the term peer-to-peer was coined. I'm the original creator of the Freenet network that some of you may have heard of. Oscar has also been involved in the Freenet project since the very earliest days. The goal of Freenet, for those not familiar with it, is to create a peer-to-peer network which allows the anonymous publication and consumption of information. In effect, somewhat analogous to a World Wide Web where nobody can tell who is publishing what and nobody can tell who is reading what information. Freenet is designed for usage in countries such as China and other countries where repressive governments attempt to censor the internet, and it's designed to allow people to circumvent that. One of the things that we've realized, however, is that Freenet's and similar peer-to-peer networks' current architectures are useless if the act of running the peer-to-peer software itself becomes or is illegal and punishable. Future peer-to-peer networks designed to operate in hostile environments may need to limit which peers a peer can connect to in order to prevent a potential attacker from essentially getting a list of all or a subset of the peers in a peer-to-peer network. The big question is, can a network like that be useful? What exactly is a peer-to-peer network? It's quite a general term, and people use it to describe all sorts of diverse architectures. Probably the most useful definition of a peer-to-peer network, at least for me, is a system whereby you have information spread out amongst a whole load of computers that are distributed, geographically distributed, and in some way networked together. People want to be able to retrieve information, so you need a way that they can search for the information they want and that it can be found for them, and that mechanism should ideally be scalable and robust. So some peer-to-peer networks, the simplest, are centralized. They essentially operate in pretty much the same way that Google does. They maintain a centralized server which keeps track of where all the information in the peer-to-peer network is. And if you want to find a piece of information, you contact this centralized search engine, and it tells you where to find the information. And you can then, in a peer-to-peer way, contact the peer with the information and obtain it. Some peer-to-peer networks are semi-centralized, the archetypal example being Kazaa, whereby instead of one centrally operated index or search engine, you have numerous search engines distributed throughout the network, and typically they're called super peers or super nodes, and they will typically just be running on some poor person's computer who happens to have a reasonably fast connection and whose computer is up most of the time. Other peer-to-peer architectures attempt to be completely distributed, so they don't rely on any form of centralization. In effect, every peer in the network is treated as an equal from a functional point of view, and somehow in such a network you have to find an efficient way through which you can search for and retrieve information. Freenet is one example of such a network. So back in the 60s, a guy called Stanley Milgram conducted an interesting social experiment whereby, and some of you may have heard of this, whereby he got got the names of a small number of people in Cambridge, Massachusetts, I believe it was, wrote their name and address on a letter, and gave those out to a couple of hundred people distributed in various states around the United States. And their instructions were that they were to try to get these letters to the intended recipients, but they could only get those letters to those people by giving it to someone they knew personally, who in turn would give it to someone else. So the first person might think, okay, well, I've never heard of this guy, but he's in Cambridge, Massachusetts, and I have a cousin or an aunt who lives near there, so I'll send it to them, and so on. And what was interesting is that Stanley Milgram discovered that for those letters which arrived, and that's kind of a bit critical, but for those letters which arrived, they would typically make it on the order of 5 or 6 steps, which in a country of 270 million is quite impressive. Most, if not all, scalable, decentralized peer-to-peer networks rely on this same small world principle, small world phenomenon, in order to retrieve information in a completely distributed way. One of the things you'll notice about the Milgram experiment is that it relies purely on individuals, ordinary individuals, and each of them is pretty much an equal in the network. Each has a little bit of information about other people in the network. Nonetheless, they're actually able to get a letter from one part of the US to a specific recipient in an impressively short amount of time. Okay, so Milgram showed that people tend to form these small world networks. More generally speaking, a small world network is any network where you've got nodes connected together in such a way that it's possible to find a short path between any two given nodes in the network. Milgram demonstrated that human relationships form that type of network. The issue is, of course, even that you may have a network in which you know that those short paths exist, it leaves open the question of how do you actually find them? So in other words, it's not sufficient just to have a small world network. Your small world network must be navigable. If you go back to the Milgram experiment and think, well, how are people navigating this small world social network? They're essentially doing so using a concept of similarity. They have a way that they can look at two peers, two people in that case, and decide how similar they are. And the algorithm they then follow is simply they look at the people they know, they look at where they're trying to get to, and they will send the request or the letter to whoever they know is closest to the intended recipient. The basic thing which makes these networks navigable is that peers which are similar are more likely to be connected to each other than peers which are dissimilar. So in the case of a human network, if you and someone else happen to live very close together, you're a lot more likely to have a social connection with them than someone just randomly selected from the global population. So the algorithm, again, is pretty simple. You just route towards, at each step, you route towards whoever is closest to your intended destination, and this is called greedy routing. So Freenet and distributed hash tables both rely on this technique. Well, for the purpose of this talk, we're also going to kind of talk about two other categories of peer-to-peer network. Light peer-to-peer networks, or you could also call them promiscuous peer-to-peer networks, are networks where peers are willing to connect to or form relationships with complete strangers. Most peer-to-peer networks today, certainly most popular peer-to-peer networks today, fall into this category. The advantage of this is that if you do it right, it's I'm not sure about easy, but it's certainly possible to make them scale properly. You can form these small world networks which conform to this requirement that similar peers are more likely to be connected to each other. The disadvantage is that they are vulnerable to harvesting. People you don't know can discover that you are part of this network. If it's a good anonymous network, they won't know what you're doing, but they'll know that you're part of it, and that in itself may not be acceptable. The alternative to these light or promiscuous networks are dark or friend-to-friend peer-to-peer networks. In these networks, the only people your peer will communicate directly with are people that you have decided you trust, people you've decided that you don't mind if they know that you are part of this network. An example of this is a piece of software called Waste. It's not that widely used from what I can determine. The disadvantage of something like Waste is that these networks tend to be very small, maybe 5 or 6 people, and they're not connected to each other. So you only really get to communicate with or exchange information with, 5 or 6 other people, and that's not all that useful, and that perhaps is one of the reasons why Waste is not that popular. Okay, so I'll let Oscar take over from here.
Okay. So the question now is, we want to take these dark networks and make them more useful, and we want to use this theory of small world networks to do it. So the question is, how can we apply this theory that Ian talked about before of small world networks to the dark peer-to-peer networks to make it more useful? And the essential realization that we need to start off with is that this dark peer-to-peer network, which is just people forming these encrypted connections with people that they know, this network is in itself just what they call a social network. It is a network of people's friends, their trusted relationships. So this is exactly the type of social networks that sociologists and psychologists like Milgram have been experimenting with, and that the whole small world phenomenon is about. And then, as Ian mentioned, from this Milgram experiment, we know that people can do a very good job of searching and routing in these networks. They can find a way from one point to another in a surprisingly short number of steps. And if people can do this, then we should hope that perhaps so can computers. And to start off with, we need a model for how this kind of the navigability arises in small world networks. And this model was provided in 2000 by a Cornell professor named John Kleinberg, who showed what dynamics are necessary for a small world network to be navigable. And what he showed that for there to be possible to route efficiently in one of these networks, you need to have a certain balance between the connections of different lengths, meaning that there should be relatively few connections that go very far, but rather many ones that go not so far, meaning, as Ian said in the Milgram experiment, where you had somebody out in the Midwest and maybe links all the way to Cambridge would be very few, whereas links going only a few cities, people knowing each other a few cities, would be much more common. So there needs to be this balance of that you know a lot of people who are close to you and then sometimes you know somebody who's far away. And if we then were to say that the positions of people were in a ring, so we have this one-dimensional space of people for the model, and of course people don't normally exist in a one-dimensional world, so you can do it in other dimensionality, but the sort of a ring is the most simple way that we can just place people and say that two people who are just next to each other on the ring are one apart and so on. And for the model to work, we then need in this ring connections to be so that there are half as many connections of double the length. So the probability that you have a certain connection, that two people know each other, will be inversely proportional to the distance between them in this base model. So here we have the red link and the green link, and the red one covers double as many people. So the probability that the two red nodes here would know each other, or the two red people would know each other, should be half of the probability that the two green people know each other, because this one covers double as many people as the green one does. And this is exactly the balance that is necessary for routing to be possible. And in this case, it can be shown mathematically that if you have this balance, you have few long connections and many short connections. If you have this balance, then you can do greedy routing in the order of log squared n steps, which non-mathematicians might not care so much. But in general, when stuff is log, it's good. So greedy routing in log n squared steps, that's considered good. That means that as the network grows, it doesn't take that many more steps to find your destination. We double the network size, it might just add a couple of extra steps. So the way that greedy routing would look like this. So now I have this model here. I've placed individuals in a circle. I'm imagining that they live in some sort of flat world, these people. So they're placed in a circle, and they have these lines which represent people who know each other. And you can't really see it from this picture, but there are a lot more lines along the edge here where it's common that people know each other, and fewer long connections because people know each other far apart. So if we wanted to go from one of the red people here to the other one, then you end up doing this greedy search that Ian talked about. You're just stepping to the closest one all the time, and it would look something like this. As you can see, you start out there in the left one, and then it takes a long step to get closer, and eventually it sort of narrows in on him. And these are the kind of routes that then generally go in log squared n steps if you have this model. So, but the greedy routing essentially, as Ian said, rests on trying to find if one person is closer to the destination than another. And if we have these people who live in this flat world on the circle, as in this idealized model, it's very easy to say, well, everyone has a position on the circle, so we know where our destination is, so if we were looking at who's closer, it's just to say, count the number of steps along the circle, and we can find out who's closer. So we can do the greedy routing. But in a social network, you don't have this information in general, because you end up having to answer questions like this. Is Alice closer to Harry than Bob? So this means we're trying to get this message. We're part of this Milgram experiment now, let's say, or we are trying to route in this darknet, as is our application. We want to get to Harry. We know we want to get to Harry, and we have two options. Should I send the message to Alice or Bob? And the question is, who of them is closer? And somehow we need to determine this closeness in order to perform greedy routing. And if we can't do this, we can't greedy route, we can't possibly hope to get anywhere. So we know that the people in the real-life experiments and the Milgram experiments and the like actually did this. And presumably what they did was that they used a bunch of factors. So the most obvious one, as Ian mentioned, would just be where people live. Somebody who lives close to somebody else would be considered closer. But there are also other things that you would, if you were trying to answer this question and you happen to know all Alice, Harry, and Bob, you'd probably take more other things into account. You'd say, where do they live? What are their jobs? What are their interests? And in fact, the sociologists have determined that in the Milgram-type experiments, it's these first two that are the most important, where they live and what they work with. That tends to be what people would use to try to determine closeness between people in a social network. But in practice, we want to build something that roots in the social network, in the darknet, and we want it to be a computer. And we cannot in practice ask a computer to route based on all this stuff about personal information. I mean, I suppose you could try to say, okay, in your peer-to-peer client, you actually have to write in all your personal information, and then we'll try to, route based on who's closer to our destination. But that isn't really practical, and we're trying to sell these things to some pretty paranoid people, so they probably wouldn't be happy. Since we cannot expect the computer to route based on such things, we need to find another way of determining the answer to this question, is Alice closer to Harry than Bob, than trying to look at where they live or their personal information, because that sort of judgment is not the sort of judgment that computers are good at. So instead, and this is the critical point, we let the network tell us. We look at the network itself, and without using any other information than just the network of who knows who, we're going to let it tell us whether Alice is closer to Harry than Bob. And so, how do we do this? Well, essentially, we remember that Kleinberg's model, this model that tells us how networks can be navigable, and we think that social networks are navigable because we have the empirical results to say that they are. They said that there should be few long connections and many short ones. If people somehow are positioned in the network, we want to have most of the connections being short, and sometimes there is one of these long red connections like I showed before. And so we just go ahead and do it this way. We assign numerical identities to these people. We have a whole network of people. We'll just give them numerical identities that place them in a circle, just like this idealized flat world model that I was dealing with before. And we just do it in a way so as to try to make this Sandberg property true. We try to place them so that people who have a lot of connections between each other, who are highly likely to be connected, end up next to each other, and people who seem to be far apart in the network are far apart in the circle. And then, once we have people in a circle, we're back to the situation we were in a couple of slides ago, where we can easily greedy root based on their positions. And there's a simple method to do this. When people join the network, they would simply first choose positions on the circle for themselves completely randomly. They just take a position randomly, has nothing to do with anybody else. They start there. And then we have an algorithm where nodes contact each other, people contact each other, and then they switch positions in the circle. So somebody says, you take my position, I'll take yours. And the reason they do this is that they do this so as to try to minimize the lengths of these edges. They want to minimize the product of the length of the edges to keep many short edges and few long ones. So this would be an example of this. We now have people who've joined the network. They all have friends, and they form this sort of thing with their randomly chosen positions. And we see two people here in this picture, Mr. Green Guy and Mr. Red Guy. And Green Guy and Red Guy both have three friends, but as you can see, their three friends all chose positions on the other side of the circle. So this is not how we want our model to look, because we want few long connections, and here we have a bunch of long connections because they're far away from their friends. But if Green Guy and Red Guy were to contact each other, and they were to look at this, they might say, well, we can switch, and it'll look like this instead. This is Green and Red are the same people, they have the same friends, but now, when the two of them switch positions, we see something that looks a lot more like what we're after in our model, namely short connections mostly, but then there is one long one, for instance, there, some slightly longer, but most are short. Okay, so this is the general method, and this is the algorithm that we're going to use. And there's just some things to note. I'm saying switching is essential, which is this. When I said they join the network, I said they just choose their position randomly. And then they have to go around switching with each other. Well, one could say, why do we need to bother with the switching? They could just choose a position that places them close to their friends on the circle to begin with, and there would be no problem. But whatever happens whenever you do this is that if everyone's trying to choose positions that are close to everybody else, I think we can all kind of see what will happen, which is everyone ends up choosing the same position, or just like converging on each other, so we get this circle where all the people are just sitting in one position, and you can't root on that. So we can't have people converging on each other, therefore we need this algorithm to revolve around people starting randomly choosing a position and then switching with each other. And this is an ongoing process, which means that the numerical position on the circle that we can root towards, that we can search for, is going to have to keep changing for people. And this provides a practical problem when we're going to apply this, but Ian will talk about how one would deal with this situation. So just to go just a little bit further on the algorithm, the way that it works is like this. Two nodes chosen in some random fashion, and they decide to switch. We don't have to discuss yet what the random fashion that they approach each other is, but they find each other somehow. And then what they do, and this is a sort of the mathematical part, so those of you who don't want to see this can close your eyes or something. They calculate two quantities that I've called LB and LA. And LB, L before, would be the product of all the distances of their current friends, the distances to their current friends as the positions are currently. And then LA would be the product of the distances to their friends if the two of these people have switched their positions on the circle. And then if these two quantities, if LB is greater than LA, meaning that the product of the distances before the switch would be greater than the product of the distances after, then we want to do the switch, because this is, we're trying to minimize the length of the product of these distances. Otherwise, but even if they aren't, we switch, but with a certain probability that's given by dividing these two quantities. And doing something with a certain probability, for those of you who aren't probabilists, means that when this happens, you do it a certain proportion of the time. For programmers, you get a random number, and you do it if you do the switch if that random number is smaller than what you have divided there, than the LB over LA. So this is the actual formula written out mathematically. I don't know if anyone cares for it. I just put it up there. And for those of you who maybe are probabilists, you'd know that you'd recognize this as an application of the Metropolis-Hastings algorithm, which is one of the most useful algorithms in modern statistics and probability for generating configurations and distributions. And the idea with the algorithm is that because there's a greater chance of moving to positions with shorter connection distances, that they will tend towards configurations. As we just play along with this algorithm, it will tend towards configurations which have distances that minimize the product of the distances to people's friends. The complete product over the entire network of everyone's distance to their friends will tend to be minimized, because when we get a switch that minimizes this product, then we switch. Otherwise, we do it only with a probability that can be rather low. But because we'll switch even when it seems like it isn't a good idea, just with a low probability, there's no risk that we get stuck in what you might call a local minima, or something where we have a configuration that all switches look bad, yet this isn't actually a good configuration. So it's very important that one does switch even to worse configurations sometimes. So then the question is just, how do they approach each other to switch these two nodes? How do nodes that might want to switch find each other? And any method for doing this will actually work in theory. And this has to do with the mathematical theory of this Metropolis-Hastings algorithm. But any method will work, but it depends, how fast this switching will get to a configuration that works will depend a lot on this. So in practice, we can see that if people only switch with their neighbors, if people are only ever switching identity with their own friends, it won't work, because it just doesn't happen fast enough that you get the switch. Instead, you need to we just do a short random walk starting from each person into the network, and where this random walk ends up will be the person that you want to switch your identity with. Okay, so just as a demonstration, we go with some simulations here to show what happens when we run this thing. And so I have, on the following graphs, I have labeled three things. For reference, we have a random walk search, which essentially just looks for a destination in the network by walking around randomly. It isn't a very good way of searching a network, obviously. You're just stumbling around like an idiot. But it has been suggested as sort of the best way to search peer-to-peer networks by a lot of people who I think aren't idiots. So we have to have that in there as the reference. And then, as the other reference, we have what I've called the good, which is greedy routing using the original model, where we have the positions as it was generated. And this is sort of the idealized model situation. Then we take one where we have the same graph as in the model, but without knowing the original positions, and we run this algorithm to try to get people to choose positions, and we see how fast we can route in that situation. And then we look at the proportion that will be successful within log n squared number of steps. And you can see that random falls very quickly as the size of the network grows. That's the red line. Random searching simply will not succeed within this sort of log growing number of steps. Whereas the good, of course, because this is known mathematically to be true, that we do keep finding it. We have basically 99% success rate the whole time in finding it in that many steps for the good. And the restored essentially goes back. It takes us from the red line almost all the way up to the green line just by running this switching algorithm. And we can see there is a slight fall for the very big network, probably because I did not have the simulator power to run it quite long enough. And of course, the other interesting thing is not just the success, but how many steps does it take to find a destination. And you can see the average number of steps for random, even though it's succeeding less and less, the number of steps skyrockets. But in the good situation, it stays very low comparatively. And in our restored situation, we have brought the number of steps necessary to try to find one point in the network starting from another back down almost to the situation we had to begin with in the idealized model. But of course, these simulations, I'm starting with an idealized model that may or may not agree with the real world. So it's not necessarily that interesting. A better question is to look at real-world data. So what we did to grab some real-world data was we went on Orkut.com, this site that Google started about 1.5 years ago, and everyone ran away and put in all their personal information, all their friends, and then they realized, I think, that it wasn't very useful for anybody except Brazilians. I don't know, this Orkut has been overrun with Brazilians lately, if somebody logs into it. But anyway, so without asking for permission, I went there and I got about 2,196 people's records, starting with Ian. I grabbed these people by spidering the site and then just who they knew in the same set. And the way that I spidered the set, I got a comparatively dense set, so that most people had a lot of friends who were already in the set. And this is good because it tends to make these sort of situations succeed more often. And as I said, because I started it with Ian and I kind of walked out as we were doing this, we got people who were techies, programmers, and a lot of them, I don't know, I doubt, well, it's possible that somebody in this room, except for Ian, is also in the set, because we just got, it seemed mostly to be California technology workers and stuff. And as I said, there were actually no Brazilians in this set. It seems that the Brazilians on Orkut are rather disconnected from the rest of the people. And something of note about this set is the degree distribution. And with the degree distribution, you mean that the degree of a person in a network would be the number of friends that they have, also known as popularity or whatever. But the degree distribution here is very skewed. There were a couple of people, you can see that the red line advances up towards almost towards 300 there, who had very, very many friends, whereas other people had very few number of friends. And this is called a power law distribution. And it's a well-known thing that social networks tend to have this sort of distribution. But we actually haven't discussed power laws at all until now. And in our models, we haven't been dealing with the power law. But it's worth noting that this data actually has such a distribution. So then the question is, how well can this method be applied to try to search among these 2,200 people and actually just starting from somebody, try to step via their friends, just like the Milgram experiment did, to get to the destination. So also here as reference, I'll have the random search, which with this, a random search that log 2n squared, you can figure out how many steps that is if anyone's good at taking 2 logarithms in their head. It's 11 squared, right? So. But in 11 squared steps, we've got about 72% success rate in finding the people with a random search. And the mean steps that took was about 43 steps. And this is actually rather good. If you think that you have 2,200 people and you're walking around randomly, then it's actually pretty good to be able to get 72% in less than 50 steps. And the reason that it is so successful is that this power law distribution, because some people have lots and lots of friends. So when we get to them, we tend to see all their friends, even in this random situation, and we can find. So this is sort of the ideal situation for the random search. And when you have this power law distribution, a lot of serious work has been done to show that random searching really isn't that bad. So what we're competing with is sort of as good as previous methods could go. And so we're going to look and see what our algorithm does. And after running this position and giving everyone positions along the circle, we find that, in fact, we are able to get a 97% success rate in only about 7.7 steps. So we have assigned positions to everyone in this set on the circle. We do this greedy routing, just like I showed you before with the red lines, to walk along the circle, and it actually works. 97% of the time, we're successful, and on average, it takes just 7.7 steps. So if one took the median instead, that would be considerably lower. So another question then worth asking is, how much effect is this taking that we had a couple of people who knew tons of people? We had somebody who knew 289 different people in this set. How much is that doing to advance the success of it? Are we just asking 2 or 3 people to do all the searching for us? Well, in the random search, we can see that if we have now clipped the degree to 40, meaning I haven't allowed anyone to have more than 40 friends, then the random search success rate falls steeply, and now we're only successful about half the time, and it takes more steps on average as well. But in fact, with our algorithm, we are not dependent on the fact that there were these high connectors in the network. We're not taking all our queries via them. We're using the dynamics of the network itself to do the work. And so you can see the success rate is the same. The fact that we didn't have those high connectors in there adds a couple of steps, but that's not worse. So the conclusion has to be that the algorithm, in fact, will sort of take advantage of the fact that there were these popular people in the set, but it can still find routes between people when it doesn't have those people in the set.
Okay. So we've outlined the theory, we've run some experiments, both on some idealized data and some real-world data, which gives us hope for optimism that this might actually work in the real life. But nonetheless, it does raise a lot of questions about how do you implement a network like this in real life such that it's actually usable, such that people can use it in practice. What we found over the years that if you look at, for example, software like PGP, the complexity of using it, and PGP is by no means that complicated, but the complexity of using it really does tend to serve as an inhibitor to large-scale adoption. So these issues are very important to consider. Key concerns: how do we prevent malicious behaviors? What are the things that people could do that would screw up this kind of network? Examples of that would be, well, okay, you're asking people to swap with you. How could somebody potentially manipulate that process in order to prevent the network from converging to something that works? And we've explored a number of techniques whereby, for example, when you're doing a swap with somebody, prior to doing it, you can exchange information which prevents you from getting to choose after the fact whether or not you swap or not. The concept is similar to how a group of people would collectively choose a random number such that no subset of those people could manipulate the result. And we can elaborate on that just in questions. How do you make sure it's easy to use? This is a real challenge. If you're trying to say to people, okay, well, you've got this software, you need to connect to people now. How does somebody know who to connect to? How do they know that their friend happens to be using this software, running Freenet, such that they can connect to them? How does the software spread? If people just go to our website and download it, but then they're told they need to know other people who are also running the software, well, that's no good. Most people aren't going to have personal friends also running the software. So this leaves open the possibility of spreading the software in a different way, in a viral way, whereby somebody gets the software, they then send emails to their friends which perhaps contain some information about where they can download the software, and then perhaps a PGP-style block of data that they can cut and paste into the software that will allow them to connect back to their friend. Other possibilities are offering trusted third-party services. which in essence act as matchmakers. This, of course, is somewhat defeating the point of a darknet, but the thing is that many people won't necessarily have the degree of paranoia that would preclude them from being willing to talk to strangers. So we can offer, or anyone could offer, a trusted third-party matchmaking service which would make that easier to use. How does this actually work? How does it store and retrieve data, which is, saying at the outset, is really the primary purpose of most peer-to-peer networks? Well, fortunately, this is actually a problem that has been solved. It's solved by Freenet and many other networks. Basic idea is you have a way. Let's say you wanted to store a piece of data. You find some way to associate a key to that data. The key might be a hash of the data, or some other cryptographically generated number that uniquely identifies the data. You can then insert it into the network, which would send a message which would try to find a peer that has an identity that is close to the key of the data that you're inserting. That peer would then cache that data. Indeed, all peers which forwarded this insert request would cache the data in a least recently used cache. Then when you want to retrieve a piece of data, given its key, you simply send a request towards the node whose identity is closest to that data, and when you find that node, chances are if the data has been inserted, they'll be caching it, and you can retrieve it, and that should then be cached on the peers along the return path to you. So it's a simple way that you can implement, in effect, a hash table using this mechanism. It's not guaranteed to be able to retrieve data, but it will work most of the time. So what are the threats? Selection of identity to attract certain data. Let's say you're interested in censoring a particular type of data, if it's possible for you to choose your node's identity, then you can choose an identity that is close to the key for the data you want to censor, and then when someone inserts that data or when people try to request it, you're quite likely to see those requests, and you can then do nasty things such as say, oh, I'm sorry, the data doesn't exist, even though it might well exist elsewhere in the network. Also, there is a danger that you could, through these swap requests, manipulate other people's identities. I alluded to that earlier. How do we ensure ease of use? So the first thing is peers will need to be always on. Fortunately, with the proliferation of broadband, that isn't as onerous a requirement as it might have been a decade ago. Peers need to be introduced, as I spoke about earlier. One option to that is using email. Other options exist, including trusted third parties, or indeed phone. What about NATs and firewalls? One of the biggest problems that has been encountered by peer-to-peer networks is that more and more people now, their computers are sitting behind NATs and firewalls, which will typically refuse incoming connections. That's not a good thing when you're trying to build a peer-to-peer network where peers need to talk directly to each other. Fortunately, techniques have been developed which can get around this. One example is UDP hole punching, which is used by Digger, another piece of open source software I developed, and Skype, which is a popular voice over IP application. I won't go into the details of that. You can look it up. It's pretty much common knowledge these days. The problem with that is that for two peers which are not currently communicating, if they want to use UDP hole punching, they need some third party somewhere that they can both communicate with in order to negotiate that connection. So that is a challenge there. And again, trusted third party can be one solution to that problem. with the email solution, email can perhaps act as that out-of-band communication channel through which these peers can talk to each other. Okay, storing data. So this is pretty much what I've said already. Yeah, so it's not, actually, yeah. So in addition to storing data, it also raised the possibility that we could establish a direct line of communication, actually indirect line of communication between two peers, and that could be used for things like voice over IP, if it's fast enough, or instant messaging. All sorts of very interesting things open up there beyond simple storage and retrieval of data. In order to do that, it's fairly straightforward if you know the other peer's identity, because then you can route a message towards them, they can route a message back to you, and you can establish a communication channel. Problem is, of course, identities change. So a solution to that problem is to employ a crossing paths approach, whereby the peers agree on a identity, and they each route towards that identity, and the chances are there's a high likelihood that those messages will cross paths. Wherever they cross paths, that peer will in effect allow those two peers to form a indirect connection through that. So am I doing the clue? You can do it if you.
Okay, so just as our concluding remarks now, we want to say that we actually think that it's possible, given this fact, to build a navigable, scalable, workable darknet that can be global in span, not just small connected small networks of friends having encrypted channels between each other, but actual globally spanning encrypted network where people are only connecting to their friends, yet we can find paths in it efficiently from one side of the world to the other. And of course, since we believe in this, we also intend to do it. But in truth, this is just the beginning. There's still a lot of work left to do. And this theory that I presented, or that we presented earlier, is still in its infancy. So there's still a lot of work left to do there. One question is, can other models work better? So the whole time now, I was working with this model, when I was talking, I was working with this model of placing people in a circle. And that was the very simplest way of trying to give people positions in the network. But of course, one could try to give people positions in a two-dimensional world, because we say, oh, well, the world is two-dimensional, the Earth is flat. So that might work better. Or we might say, well, we live in cities, perhaps it should be three-dimensional positions. So one needs to explore all the different kinds of models to find what actually works best. And to do that, one needs to look at larger data sets and more data sets. And one critical question is if we can find better ways of selecting who to switch with. So if you remember, the algorithm rests on the idea that people choose positions randomly, and then they go around switching with each other so as to try to find optimal positions for themselves. And one of the problems is we're currently, as I said, randomly, through a random walk, deciding who somebody should approach to try to switch with. It's better if we could find more targeted ways of doing this. This will allow the convergence to the correct configuration, or to a good configuration in a smaller number of steps. But there are mathematical problems with doing this sort of thing, intricacies and somewhat subtleties that one needs to deal with when one gets to a more targeted situation. But certainly that would make the algorithm perform a lot better and more efficiently if we could. And obviously it needs to be tested on more data. 2,000 people that we borrowed from Orkut one night is probably not, the world's best set to test it on. So we need to do more tests to make sure how well this will actually work. And one doesn't really know, as Ian said, with the deployment and all that, we don't really know how the network can actually look. And it depends a lot upon how it's deployed, if it's easy, etc. So we're in dire need of a lot of data to test all this on. And beyond the fact that the theory we also know that we need to deal with practice. And we know quite well that practice is not always theory. After we started with saying that we worked on the Freenet project, and probably most of you have heard of the Freenet projects, but probably most of you have never gotten anything useful out of it if you've attempted to use it. And that was because, well, our theories have been good, but so far the practice has been perhaps not quite up there. But practice is hard, and we know sort of what we need to do to convert this theory into the practical situation. And as Ian said, we need to deal with the security issues from day one. One needs to keep security in mind when deploying this type of network, because keeping people's privacy, allowing people to communicate without being disturbed by others is what we're after. And as I said, how the network is deployed will affect how well it works, because we need this dynamics of the social network to carry through into the darknet. And if we don't do that, then it won't work. So we need very much, as Ian said, this sort of viral deployment of the network. It needs to be easy. It needs to spread to friends so that people really are there with their friends, and there really are there's connections that the algorithm can use. Otherwise, we're out of luck. But that's it, and we're continuing from this point in our work with this. And most of the discussion is going to be at freenetproject.org. So if anyone is interested, that's where the action is. We have, I don't know. I think we can just take questions again.
So if anyone has any questions, we've got about 15 minutes. We can take those. Yes, sir.
Just like to comment on the disappointing Grokster vote from our Supreme Court.
Well, that's a bit off topic, so maybe we'll talk about that afterwards.
How do you do with the addition of mobile units, mobile nodes on your server, right?
Mobile nodes in the sense of laptops, people whose IP addresses changed,
Yeah.
that type of thing. Well, right. Well, it adds complexity from the point of view of when someone changes IP address, reestablishing their connections with their friends. If their friends are all on open IP addresses and can accept incoming connections, then it's actually not that big a problem. If their friends are behind NATs, then it's more of a problem because you need some way to negotiate the connection with them. But that's pretty much the same problem as you have at the outset anyway. Solutions to that would include a trusted third party. I don't know if you want to comment.
Well, I'd say actually that these type of networks are almost better suited for that type of situation than the kind of promiscuous peer-to-peer networks that you have right now. Because people really, I mean, in this situation, the base graph of the people, the base network, is fixed. You're just connecting to your friends. So it doesn't matter where you're connecting, because when you come online, you're interested in your friends. And okay, there can be a problem in the sense of, well, you've switched, your friends switched, you can't find each other again. But it tends to be, I mean, because people tend to have the same friends, there are ways of dealing with this. So if you just look at, for instance, the darknet in Nullsoft's waste, that tends to work very well even with people, just because some people in a sort of social sphere will tend to be online at any given time and they can keep track of one another. So I'd say that because of the fixed graph and the base, it actually deals pretty well with that sort of situation.
Any other questions?
Just a statement about what you said. In your model, think about it in terms of people with mobile systems and the fixed basis that they're mobile in. Try your model with multiple personalities where you have a set of friends.
Yeah, okay, you could have that problem that people have the multiple clients, you mean, and sort of appear as multiple identities.
The person with a mobile connection in a social network like this would have multiple personalities. It's kind of like, who are my friends in my day job, who are my friends in my...
Yeah, okay, so that goes back to the sort of the dynamics of the social network. And of course, this model, the Sandberg model, which just the fact that everyone has one position and they have short links and long links, it's simplified, of course. It's an idealized model and simplified. And of course, you have the situation people belong to several different social groups and all that. And that's the sort of thing that you need to deal with when trying to apply this model to real-world data. But as I said, so far it looks, I mean, that sort of data will appear in any, I don't think it's very important, it just has to do with this mobile connector. Any social network will have that sort of thing. And of course, our basic assumption rests upon the fact that the basic idea that you're trying to minimize, trying to keep most connections short, will still be sort of fulfilled by this, even if the dynamics are not perfectly in line with the model.
I would say, I mean, my suspicion would be that the properties that we need of a network in order for this to work would actually survive, would actually still be the case even in the situation where you describe, where people tend to have multiple social networks within which they operate. It's actually a very robust property, but that's a good point.
So how would your proposed file change network specification framework? How would that compare to something like a tracker?
A BitTorrent a BitTorrent trackerless or no is still what you would call a light or promiscuous. You connect to a tracker, you're still sending your IP address to everyone else on the tracker. I mean, okay, we're trying to be a little bit legit here, but we know what the problem is of sending your IP address to when you're sharing some data. Somebody might come after you with a bill.
Also, I mean, the other key thing, and perhaps we glossed over it, but one of the goals of Freenet, both currently and when we implement this, is to provide anonymity to users. BitTorrent, trackerless or not, at least to my understanding of it, doesn't try to do that. It doesn't seek to provide anonymity to users. So.
Yeah. So, I mean, going trackerless for BitTorrent is moving. I mean, where we started out was we said we can have decentralized networks, but we want to take it one step further. So BitTorrent is really just getting to the decentralized point with the trackers going away. And it certainly doesn't have this property that you actually are, that the network is actually invisible, that your participation in the network can't be found by people. Yeah?
If you introduce a trusted third party, isn't that just the way to attack the network?
Well, so it's up to the user. What you're doing is you're giving more options to the user. So you're saying to the user, you can trade convenience for security. And so you're really just, if it's important to the user that only their friends know that they are part of the network, then they have the option to do that. If that's not important to the user, and I suspect in practice there will be a lot of people who don't actually care, then the option is open to them to use a trusted third party. So you're putting really the control is in the hands of the users there. Any other questions? There's one right at the back there. So what is the advantage of this over putting your IP address in a DHT? Well, a basic answer, maybe I'm not quite understanding the question, but DHTs are promiscuous peer-to-peer networks. So DHTs fundamentally rely on being able to connect to strangers. So if you have a reliance on a DHT, then it is not a dark peer-to-peer network, which is the thing that we're trying to create here.
So a DHT, distributed hash table, it's these ways of building these networks in a way as to make them routable. And there are ways of doing this, and those ways revolve around selecting your friends or your neighbors in the network after certain algorithms in certain ways, and that will dictate who you have to connect to. And that can't be just your friends. The whole idea with what we're doing here is we're saying social networks form a natural DHT, we just need to unleash it. So trying to build a DHT would be completely counter to what we're doing, because we want to use the natural one so that there are only ever connections between people who know and trust each other. No, when they swap, because the people introduce each other to swap via a random walk. So you just keep a tunnel open, and then the swap will happen over that random walk tunnel. The random walks in question are 3 or 4 steps. They're not long. So it would be easy to keep a tunnel there. So they would not have to know each other's IP to do that. Well, to do the swapping, everyone has to be online. But
well, the person you swap with needs to be online, but you wouldn't find them if they weren't. So it's not really a problem.
As long as you assume some sort of that people's online habits don't depend on their identity, which it's not going to, since the identity starts at random. It's not going to matter that people come on and off with the...
Any other questions? All right then.